Hi, I'm going to go over the explanation for the Bonding and Molecular Structure Quiz 2 free response problem. So let's get started. Part A tells you about an equation between SF4 and BF3. And then the first actual question, part I, asks you to draw the Lewis structure for the ion SF3 plus in your SF3BF4 compound. So let's go over drawing this Lewis structure. The first thing that I do is count up the valence electrons. So sulfur has 6, plus each fluorine has 7. I need to multiply that by 3 since there's 3 fluorines. And then that cation, the plus, means we've actually lost an electron. So from this count, I need to subtract 1. So let's see, 7 times 3 is 21, plus 6 minus 1, that's going to be a total of 26 total valence electrons. So now that I have my count, I place my atoms and connect them all with single bonds. So in here, I know sulfur is going to be the central atom. That way this molecule would have some symmetry with the fluorines around it. Sulfur is also less electronegative than fluorine, so that's why it's going to go in the center. So I would put sulfur with 3 fluorines all around, and I need to at least connect those with single bonds. So now back to my valence electron count, I think about how many electrons I've just used up. So each bond is 2 electrons, so 2, 4, 6 is what I've used up in my bonds, leaving me 20 electrons to place around. So that's what I will place around with my lone pairs. So I just go around counting up to 20 and I'll stop when I get there. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So I've used up all the electrons I have, and now I just need to check, does everything have its octet fulfilled, or do I need to move anything around, creating double or triple bonds? So if I check, those fluorines all have 8, right? 2, 4, 6 in lone pairs plus 2 more shared in the bond makes 8. And then the sulfur as well has 2, 4, 6, 7, 8. So everything is good. There is one last step to this Lewis structure because it was an ion, and we do need to indicate that. So how you indicate that is you put the entire structure with brackets around it, and then you put the ion charge on the outside. So that would be our Lewis structure for SF3 plus ion. Part 2 asks us to identify the hybridization exhibited by sulfur. So what I look at here is sulfur and how many things it has around it. So I count 1, 2, 3, 4 things around it. 3 bonds and 1 lone pair of electrons makes 4. So anything that has 4 things around it needs sp3 hybridization. And an easy way that I remember that is just counting up to 4 again. So S is 1, and then P, 3 P's is 4. So that's how I remember the hybridization. Part 3 asks to identify the geometry. So part 3, now we're looking at the geometry. So again, we come back to sulfur, the center atom, and think about how many things are around it. So there were 4, right? So it's a tetrahedral type shape, but we don't have 4 atoms. One of them is actually electrons, so we don't see them. So what shape this ends up making is trigonal pyramidal or trigonal pyramidal. Okay, and then the last part in A, part 4, asked to predict whether the the FSF bond angle. So this bond angle right here between the S's and the F's, is that larger than, equal to, or smaller than 109.5, and we have to justify our answer. So in a normal tetrahedral geometry, if we had an atom down here, those bond angles would all be 109.5. But since we have this lone pair of electrons here, it actually takes up more space because it's repelling away even greater. So what it does is it squishes those other bonds in tighter. So this bond angle is actually going to be less. So I would say something like the bond angle will be less than 109.5 degrees because the free, or really the lone pair of electrons causes more repulsion thus pushing the fluorines away and causing the decreased bond angle. Okay, so now let's move on and talk about part B. So part B, again, gives you an equation, but then it ultimately just asks you to draw the Lewis structure for SF5 minus the anion in CSSF5. So again, we're going to do the same thing. We start by counting valence electrons. So a sulfur has 6 plus 5 times the 7 that each fluorine has, plus 1 extra, because that's what the -1 charge out here means. So if we add all of that up, I have 42 total valence electrons. So again, I'm going to look here and I'm going to decide that the sulfur is going to go in the center, and I'll place my 5 fluorines all around it. So I'll do my skeleton like that. 1, 2, 3, 4, 5 fluorines. And at the very least, they have to all be connected by a single bond. Okay, so now I've already, of these 42, used up 10 electrons because I wrote 5 bonds. So the electrons I have now to place around as just the dots, as the lone pairs, is 32. So I'm just going to start fulfilling octets, moving all around. And I'm going to stop when I get to 32. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. And I still have 2 more, so I'm going to place those on the center. 31, 32. Okay, so now again, I'm going to check. I know I can tell all my fluorines have an octet, and then sulfur actually has an expanded octet, which is okay because it is in energy level 3. And remember, anything in energy level 3 or above can have an expanded octet because it has those d orbitals available to hold in those extra electrons. So again, we're almost done. This is an ion, so the whole structure needs brackets and the charge on the outside. Okay, so number 2 asks us again for the hybridization. So hybridization of sulfur. How many things are around it? 1, 2, 3, 4, 5, 6 things are around it. So I need a hybridization that goes up to 6. So I have S is 1, P3, that makes 4 total. I need to now go into the D. If I had 4, 5D2, now that's 6, right? 1, 2, 3, 4, 5, 6. So that would be my hybridization on the sulfur in this particular structure. Okay, part 3 is now asking for the geometry. So something with 6 things around it, that's the octahedral type structure, right? So really what it looks like is you have something up, something down, and then you have 4 things all around it. But in this case, we don't have an atom up and an atom down. One of these is just electrons, so we essentially can't see it. So now what this shape turns into is a square-based pyramid. And this one here in my picture is upside down since I drew the electrons on the top, but you could also imagine it going the other way, so it'd be a pyramid pointing up. So that's where this shape is square pyramidal. Okay, and then the last question, part 4, asks for the oxidation number. And they want it of sulfur in CS SF5. Okay, so this on its own would be a bit more confusing, but the problem has given us a really big clue. It's told us in this compound that this SF5 is a polyatomic ion, right? So I can just look at SF5 minus, because that's the ion it told me it was. The other way we could have told or known that that had a -1 charge is looking at cesium. Cesium is an alkali metal. It always has that +1, so that's how I would also know that that has a minus. But I'm just going to break it down into this. So I know that whatever the oxidation number is of sulfur plus 5 times the oxidation number of fluorine has to come out to equal -1, because that's this overall charge. So what I don't know, what the question's asking me to figure out, is sulfur. So I'm going to say that's X, and I'm going to solve for it. Plus 5 times fluorine is a -1, right? It's in the 7th column, or the 17th column, and it's a -1. And here we also know that we would take fluorine's oxidation number for what we expect, because the question's asking us about sulfur. So we know this is going to be the one that we need to figure out. So all that has to equal -1. So now I essentially have an easy algebra problem. X minus 5 equals -1. So then that must mean that X is +4. And that's our oxidation state of our sulfur. So the full problem here, right, you had to draw Lewis structures of 2 ions, making sure you put brackets and the charges on the outside, identify hybridization and the geometry, and then they gave us an extra question about each of those structures. But this is a good example of a bonding free response question.